should start now. Let me start from self-introduction. I'm Greg, and I am one of the hosts of this event. And although our name is functional Thursday, but basically you can introduce any language, programming language facilities like a compiler, linker, or runtime. So today my topic is about the Firefox JavaScript engine and the SpiderMonkey. And I will introduce that its internal structure includes the two-layer JIT and the GC, and then with a real case that I tracing for 1 month. It cost a lot of time, but I learned a lot. Okay. So this is my agenda. The first topic is I will introduce the whole structure, namely the overview of our JavaScript engine. And then because the JIT is the current key feature of optimization, so I will put some content on that. And the next one, the bug bytes and empty constructor, is what is the bug I traced for 1 month. It's because it affected the performance. So the following content are all about the bug and the progress I made for that. So the first thing is the SpiderMonkey itself. Basically, if you search for the SpiderMonkey, you can see some nice picture like this, and it will introduce you that the SpiderMonkey is composed by parser, interpreter, and 2 JITs. But it's a hugely simplified version. If you take a look at the code, you'll find there are a lot of tricks inside. And I can only introduce some of them to you because it's a very complicated engine. So, for example, there is an interpreter, but the picture will not tell you. The interpreter actually put some very dirty trick inside the parser. So when the parser emit a method, it looks like connected to a C++ implementation. It actually doesn't, because it's composed by some parsing unit. So you cannot find a corresponding implementation in the interpreter, something like that. And we have a lot of cache, and the most important one is the inline cache for the baseline JIT. And it's the core part of the baseline JIT. And I will introduce you how baseline works, depends on that. And then the second type of the JIT engine is the IronMonkey. IronMonkey basically is a full compiler, means it has all the optimization strategies like the modern compilers. And there will be 28 steps from the very raw bytecode structure to the final assembly. Yeah, and that's an overview for our SpiderMonkey. And if you consider our code, it will depend each other like this. And this is also a simplified version because this picture generated maybe 2 years ago. According to the bug number, you can see here. It started from 63, but we now have 128, blah, 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 so yeah. But I now pick some interesting files for you, so if you have time and you're willing to dig inside this code base, you can find some, well, funny things inside, yeah. So, for example, there is this friend API.h. Basically, it's a header file to expose all the JavaScript function you can use inside the Firefox as internal method. For example, because we have a render engine named Gecko, Gecko will render all the HTML and its DOM elements on the page, and of course include the CSS and the animation. So some of these functions will rely on those methods exposed by JavaScript engine. For example, there is a method called get global for object cross component, which is inside a JavaScript engine because it's exposed by this header file. So in the get code, another engine, the render engine, it can use it directly. So this engine could collaborate by this file. Yeah. And by the way, I leave the link on the slide. So if you want to take a look, you can just download or open the link of my slide and click on it. Yeah. Okay. The next one is the interpreter.cpp, which is 5,000 lines interpreter in a file. So, and because of the performance issue, we even replaced the C++ switch case with our macro implementation. Because if the macro could improve our performance by 1%, it will be very huge improvement because our script will firstly be interpreted by this file. Yeah. Okay. But it's also a good start to set your breakpoint if you want to debug the engine. Yeah. And then there's a file named self-hosting.cpp. There's some tricky thing is that basically SpiderMonkey is composed by C++ and JavaScript. So we use JavaScript to write our JavaScript engine. And some of this JavaScript implementation is to follow functional yeah. The JavaScript inside the JavaScript engine is mainly because we want to follow the ECMAScript spec, but we don't want to waste our time on guarantee the memory safety and other issues that C++ may encounter. So we put JavaScript inside JavaScript engine. Yeah. And this is an example for that. There is an array.js file inside our engine, and there is array.find method defined by the ECMAScript spec. So you can see we use macro to with the exposing API with the implementation. And this implementation is totally in JavaScript. Although it's in a style of low-level JavaScript, but you can see it basically follow the spec strictly. So compared to that, I once saw the source code of the Chakra core, which is the Edge JavaScript engine by Microsoft. They don't have this part. So when you find a spec bug in the Edge, you don't have the way to follow the spec to debug the engine because it's all in C++ and it's horrible. Yeah. So basically, I think this is a good strategy and it didn't downgrade our performance too much. Yeah.
Sorry.
Okay.
I'm not that familiar with Firefox, so could you explain what SpiderMonkey and Gecko are?
Okay, it should be my first introduction. Sorry, I forgot. Okay, here's the thing. Firefox is a browser, and a browser needs to render things like HTML tag and CSS and SVG and animation on the screen. So the rendering part is by an engine named Gecko. It will implemented in C++ and it will handle all the things. And there's a small engine named Neko, handle the network request like TCP, UDP, and something like that. And the rest of one is the SpiderMonkey, which is a JavaScript engine. So it purely accepts the JavaScript and outputs some assembly to CPU and maybe GPU if you have the GPU computation, of course. So this three engine collaborated as one browser, the Firefox.
Okay.
Yeah.
Okay. That makes sense.
Yeah. Sorry, I forgot. Yeah. Okay.
不好意思，请问那 render engine 跟 JS engine 怎么互动？
就是因为前面有一点点这样的，没关系，我在讲，就是因为其实也没有，就是我们的 JS engine 它会 expose 一些 API 给 render engine 用，那它会写在这个 header file 里面。所以你这个例子说，左边是 JavaScript engine 的 那个 exposing 的那 header 里面内，就是它把这个 method expose 出去。那在 Gecko 里面就可以接到这个 method 在哪里用。对，所以 render engine 可以直接使用 SpiderMonkey， 就是 JS engine 的。Question? Okay. I think it's a boring part, but you must know these to have a better overview. Yeah. And if you want to trace the bytecode generated by the SpiderMonkey each time, you can start from this file. It is documented all the methods that SpiderMonkey will use to handle the bytecode, and it's a middle step toward the JIT engine and the interpreter, between the interpreter and the JIT engine. Yeah. So I mentioned that we have two JIT, just-in-time compiler inside our JavaScript engine, and this is the first layer, the baseline. And you can find the whole implementation of baseline in one CPP file, and you can see the entry here is the enter baseline, which will accept the compiled bytecode and some stack information as this way. I will introduce the JIT later, so this is just a quick look. And another JIT engine is IronMonkey, so it's also in one file named CPP. And there are a lot of methods, but I just put two examples here. The Iron Cannon, I don't know why they named things like this, but it's basically the enter IronMonkey method. Yeah. Just the name very confused. Yeah. Okay. And the optimized mirror is the method that you can see we use 28 steps to optimize our code inside the method. Yeah. Okay. And I mentioned the mirror. Mirror is a graph structure, and it has instruction node. So your JavaScript program will be represented in that way. So there is a 13,000 line file for mirror, and you can see all the instruction and nodes inside. Yeah. And compared to mirror, which is a middle layer instruction representation, we have another one is layer. Layer is basically adapting the CPU and the ISA, which means it can either handle the length of the integer or the character. So the mirror will be translated to the layer, and the layer will be translated to the assembly. Okay, so I basically introduced some component of our JavaScript engine, and the next thing will be the JIT. So, any question so far? Okay? Okay. If I talk too detail or you feel confused, just interrupt me. And basically, we have two layers of the JIT engine, and they in charge of different optimization. And we will take a look at these two JIT engine, and there is one interesting thing is how baseline works. And then between the IronMonkey and the baseline, there is a technical term means bailout. Bailout means when the optimization fail, you need to go back to the first layer. And the last one is some hacking tips for the JIT and the SpiderMonkey. Okay, so if you take a look at the SpiderMonkey, you can see your program has been parsed by parser and then sent to the interpret as the first execution. And if your code getting hard, means it get executed like 20 times to enter the first layer of JIT. And this baseline JIT will do some basic optimization. And then if it gets really hard, like for 1,000 times, it will get into the second JIT to do some heavy optimization.
Can we know of the engine to use JIT engine by just calling a function 20 times?
Yes, you can do that.
And I can put a special argument that will just return directly.
You mean you want to?
So it will call the function 20 times but do nothing.
That trick will not work.
So the trick does not translate the code function by function, but probably
Function is a unit, but it can optimize the loop.
So it can just optimize part of the code in the function.
Basically, we have some unit of optimization. One is the whole function, and then one is like the loop, and then some if-else branch. So there are different units and different granularity.
So how can we force the function to be?
You can use about config on your browser. Yeah, and
And I used to try the typed JavaScript, so I use
you mean type array? Oh, yeah.
A plus symbol.
If you want to try that, I recommend you to use ASM.js. It will enter the baseline directly.
I use the double code and ASM, but it was
Maybe.
slower.
Oh, maybe there's some bug. Yeah, but we can discuss that later. Yeah, but anyway, basically, if you have a script or a section of the script run 20 times above, it will enter at least the first baseline bit.
How can we cheat it that
I recommend that you at least to have one statement of new something inside the loop. Yeah, I tried that. It will enter the baseline and then I monkey. Yeah, but you need to remember to use that new instance to override some old value as a reference. For example, you have a VL full before the loop, and you update that again and again inside the loop. So it will enter the baseline and then I monkey if your iteration as many as the threshold. Yeah. Okay. So back to the slide. The interpreter basically accepts the passed bytecode and then will invoke the C++ methods inside the engine. So it's slow, but it has the great responsibility because every bytecode is corresponding to C++ method will be invoked immediately. And baseline, it will try to compile some expression or statement into assembly. The feature here is that the baseline will never fail, while the iMonkey will do some very heavyweight optimization and it may fail sometimes. So we can take a look at this picture that you can see, although interpreter is slower than the JIT engine, it still become the first gate that the script will pass by. And it's because it covers all the case. And for the baseline, only when your code get hard and only by some spatial expression it recognized. So baseline can cover only some of your script, but it's very fast. I think there is a number that it's faster 100 times than the interpreter itself. So we can do some optimization here, and then the iMonkey will turn your program to a graph, namely the mirror, and then try to do some optimization after the baseline. But sometimes it will guess in something failed, so they will bail out baseline. Yeah.
But will the baseline go back to interpreter state?
No. We in the previous implementation, we have iMonkey, and then we have another JIT engine named JavaMonkey here, and it will bail out from iMonkey to interpret. So it's very nasty because you will downgrade the performance by at least 2 rates. Yeah. So baseline replace the JavaMonkey and it keeps the correctness. So only iMonkey will bail out to baseline, but never bail out to interpret. But there's an exception. If you trigger GC, it will bail out to interpret. But that bail out is not the bail out we're talking here. Yeah. So there are some special cases. but generally you can say it only bailout to baseline. Yeah. Okay, so let's take a look at how baseline and iMonkey works. Basically, baseline only optimize the instruction or expression one by one. And the iMonkey will try to optimize the whole function or the whole control flow unit, like the loop or the branch. And baseline will also collect type information for iMonkey, because iMonkey will assume our type is correctness when it's doing the optimization. So here is why the bailout happens, because when baseline collect the type of information, it may collect not too much to make it always correct. So when iMonkey encounters such error, they need to bail out baseline. And they work in different ways. The baseline basically just put your code to match some already cached chains, and to try to match one thing that it can execute. And the iMonkey will try to trim some unnecessary instruction and do other optimization. So why type is so important for JIT engine is because, like in JavaMonkey, I mentioned that once before the Firefox 24 is the place now the baseline now has. Okay, so JavaMonkey is untyped JIT engine, so when it saw the x plus y, it needs to do a lot of guessing of its x and integer in 32-bit or other guessing like that. So every time it saw expression or instruction, it needs to do this. So it's very slow compared to the iMonkey and the baseline. Okay, so baseline works as this. When baseline saw expression and statement like this, it will try to match some cache. So this is the code inside our code base that you can see. Baseline will try to match the case as the arrays in double. For example, when you say the variable a is 3.14, it will match this part, this cache, and then you will turn it to assembly directly. So the next time the same variable be used, it will use the assembly instead of be bytecode and then assembly again. Yeah. So why it called the IC chains? Because when the first mention failed, it will jump to the next one. So there is a more general optimization cache later. They'll try to match that as a chain. It's called the IC chain. So, any problem? Okay. So the limitation here you can see is that baseline can only handle things one by one. So it cannot trim some instruction and handle the branch detection because it can only translate your bytecode to assembly. Yeah. But the correctness is guaranteed. Okay, so the baseline work as what I say, it will optimize your code one by one, and the iMonkey will try to put the whole method and the compilation unit into a graph and do some optimization according to the graph and the type of information. So let's talk about bailout. Bailout means that iMonkey guessing something wrong. So this is one graph that iMonkey will generate for your code. That you can see there's a loop, and there are some mere instructions inside the graph. And then when there is some resume point here, so when something is wrong, it will bail out the whole graph, means to deprecate the whole graph and to enable the baseline again, and then switch to the baseline until the next time iMonkey be invoked. Yeah. So this flow is generally the best flow for iMonkey. It will try to refer the method and history of the execution, and then draw the whole graph in mirror and it will optimize the graph, like maybe to train some iteration inside, and then it will lowering graph to generate the assembly and execute the assembly. But when things go wrong, like for example, when a function usually return an object, when a function return a number, when it usually return an object, there must be something wrong. So the iMonkey will try to duplicate the whole graph it compiled and generated, and then pick one resume point nearby, and then try to rebuild the frame the baseline need and switch to baseline. So iMonkey will now get sleep. Yeah. So basically, this is what the bailout need. That firstly, the iMonkey has a basic block as the graph shows, and it will find a resume point, and according to the resume point, it will try to rebuild the whole baseline frame. And so baseline can accept this frame to start over on the screen. Yeah. So, any question?
Does iMonkey needs to draw back maybe some variable value to maybe does he need to replay part of the execution in order to?
When there's a bailout, iMonkey will basically it will close some register status named snapshot. They will restore the registers for the baseline, and then from the nearest resume point to execute that frame. So there's a row graph. So for example, if our program has been compiled and the engine executed it to the T1 here, and so if something wrong here, we can start over from the T0 here. It's okay because there's only one instruction to save x as some argument, so it can be played again. And if we need to, we can play it again and again. There will be no problem. But the thing is, if there is an API call, it will do some effect, like if it is console log to print something out. We cannot bail out to the T1 or the first entry because it will redo the API call. So we set the resume point here to make sure we only bail out to the safe part. Yeah. So this is how the bailout works inside our engine. So you can use Snowflake to test your program if you care about the performance. You can see like after our browser start in the debug version, it will bail out 50 times. So it means that iMonkey gets something wrong at least 50 times, and then it will cost some performance each round. Yeah. So, any question? So basically, you can just image out the resume point as a checkpoint like in a video game. So when you die, you respawn at the checkpoint that you made. Okay. So this is the overview of our two trees, and I think that for the hacking tip, I just want to mention one page that's on our development network. You can find all the instruction here you need to hacking the engine, and it's growing, so there will be new tips on that. Yeah. And for example, you can disassemble your JavaScript function inside our JavaScript shell, which is the one you cannot do in our browser. So if you have a JavaScript build, you can do that. And we have some inspector to let you take a look at the assembly generated, but generally you want to dig into the assembly because it's too complicated. Yeah. Okay.
You have mentioned that there is some part of the function that is written in JavaScript, like the array find example.
Yeah.
Will that JavaScript be executed by baseline directly, or will it be precompiled?
That's the interesting part because we treat it as the ordinary JavaScript. So it will follow the same path to the parser, and then the interpreter, and then the baseline, and then iMonkey. And the iMonkey will get strong about our self-hosted script too. So that part is very weird, but it works as the ordinary JavaScript. Yeah.
But if that is the case, can we write that sort of low-level JavaScript in our script file?
I don't think so because that script rely on a spatial environment named self-hosted. So they will provide some very low-level functions inside that environment. So that part is not exposed by the browser.
Okay, about the bailout part, if we write something that does many side effects, like printing many messages,
Yeah.
so will that cause the iMonkey to insert many checkpoints?
Yeah, it will set as much as the checkpoints as your API calls or function calls. And then every time you want to write some value to memory and read the memory, it will set a checkpoint too.
So if we write something that is more functional, it's possible that the thing runs faster.
Yes, I think so, but maybe we should do some experiment. Yeah, that's a good point. Yeah. So yeah, I think that's worth for experiment. Yeah. But the point is, it's even fragile that if you write something to memory, it will do some checkpoint for you. So maybe not works as we imagined. Okay. So the next part there will be a real case that I debug for one more. So would you like to take some rest in 10 minutes? No? Okay. Okay. So anyway, okay, here's the bug. If you want to take a look, you can just find this bug on our bug design. Basically, it describes a case that we have two loops here. One is with a contractor with two members, and one is without a member. And the loop is very a lot of times. And you can see the empty one text is longer than the one with members. So there must be something wrong, right?
Because it checks all the time. It checks many conditions all the time.
The final result is that it's relevant to the GC. But a lot of time, when I first saw the bug, I didn't know anything. So I do some inspection. Okay, so there's the internal, well basically the open source, but it's still internal use that named the Gecko profiler. You can use that to profile the whole program, and it will show all the states, include the JavaScript part and the C++ part. So you can see here, and this is the sensor inside our browser. Basically the Gecko and the SpiderMonkey. And the script itself, like this one, is basically the script. So you may see some JavaScript.js here. And we use this Gecko profiler when we have no idea about bug. And it will list the case as the timeline. So you can click here to see what is this. For example, if you click on that, it may indicate that the method called here's the GC. It's complicated to use for the front-end developers, but it's useful for debugging our browser.
And what is the bottleneck?
Oh, you mean this?
And what is the bottleneck? So why there's why it takes more time to compile for the one without constructor? So where's the bottleneck?
You mean a case?
Yeah. So where's the bottleneck? Where is the key point? What's the
The
critical
key point is the GC, because our GC has a 2-layer unboxed